Hello everyone, my name is Yan. In this video, I'm going to talk about some of the predictors of hearing aid benefits for speech perception in noise. The rationale of a larger study that I'm doing is that hearing aid users sometimes have very different experience in terms of aided benefits, even if they have similar audiograms. So we want to know what then predict the aided benefits if not audiogram. For this presentation, I'll lean more on the electroacoustic side, the HASP. Just very briefly about the participants and the tests we did. 35 older adults with mild to moderate sensorineural loss were recruited. They were examined and tested with audiometry, MoCA, which is a screening tool for early cognitive impairment, and IPASS, which is a suprathreshold test battery to examine frequency and temporal processing, envelope detection, and binaural hearing. And lastly, QuickSyn, which is a clinically used speech-in-noise test. For a QuickSyn task, you need to repeat what you heard. Speech is always from the front, with babble noise at different locations. There are 6 target sentences of decreasing SNR in each run. 5 words per sentence, so that's 30 words in total per run. We did this for multiple conditions. 2 chambers, high and low reverberation, 2 hearing aid directional microphones, omni and front fixed. 3 noise configurations including front noise, 90-degree noise depending on better ear, or surrounding noise. This setup was later replicated in KEMAR measurements, so that we have audio recordings of exactly what the participants heard. HASP was then calculated using those audio files. Very quickly on how HASP was calculated. So we took the better ear channel of the recordings and compared with the clean reference. We made sure that calibration captured the correct dB value for level 1, which tells the HASP function to listen to both the clean reference and the test audio at a physically meaningful level, so that we can also take hearing loss of the participants into consideration. Moving on to the results. First, let's see how QuickSyn and HASP correlate with each other. Panel A is the mean plot. Other panels are just colored differently to highlight comparison of conditions. Y-axis is how many words did the participants got correctly with a range of 0 to 30. X-axis is the HASP score of the corresponding stimuli with a range of 0 to 1. You can see in panel A, there's a moderate overall correlation at about 0.6, which is statistically significant. In panel B, yellow dots are high reverberation data, blue dots are low reverb. You can see the 2 clusters are clearly separated from each other, and the high reverberation really messed up the correlation. In panel C and D, directionality and noise location did not have a significant impact on the correlation between HASP and QuickSyn. And then, if you take the difference between conditions, you can derive benefits. For example, if you take the score of using front fixed directional microphone minus the score of using omni microphone, then you will get the directionality benefit, which is shown in panel C. For the same manner, spatial release from masking benefit was also derived, shown in panel D. Panel B is the combined benefit of the 2. Panel A is putting everything together. You can derive these benefits using either participants' QuickSyn scores, which is on y-axis, or derived by HASP scores of stimuli, which is on x-axis. Interestingly, almost all of these correlations are lower than the previous slide, which suggests that you don't want to use one type of the score to substitute the other, especially when representing aided benefits. Okay, previously we looked at individual level difference between HASP and QuickSyn. Here's a group level comparison. Both QuickSyn and HASP captured the direction and magnitude of each acoustic manipulation which are a large reverberation penalty, a consistent directional mic gain, and spatial release from masking benefits that reflect Haspy's better ear model. For example, you can see this spatial release from masking benefit was captured by Quixin, but not by Haspy, because the SNR for the better ear model in surrounding noise is most likely not better than the SNR with front noise. But human beings use 2 years to benefit from this. Now, let's see how Haspy contributes to the prediction of aided benefits. First, let's fit a linear model of the benefits using a single variable, pure tone average, representing the audiogram. Then take the residual, which is the portion that cannot be explained by audiogram. The portion that can be explained by the audiogram is noted by the dark blue bars. Y-axis here is percentage explained. X-axis contains different types of benefits. Secondly, fit the residual using Haspy. This is to test if Haspy can contribute more after controlling audiogram, noted by yellow bars, which are visually too short to see. And thirdly, same process with the superthreshold test battery, the I-pass, noted by red bars. The take-home message here is that superthreshold tests explained a significant portion of aided benefits after controlling audiogram. If we fit the benefits directly with Haspy, then you can see it does explain a few percentages, but got dominated by PDA according to the residual model. For conclusions, Haspy captured the direction and magnitude of each acoustic manipulation at the group level, but had limited utility for individual level prediction of hearing aid benefits in this study. Superthreshold abilities stood out in predicting hearing aids benefits. That's all for the video, and thanks for watching.